Hello, this is Keith Jackson, Director of System Integration at Rigetti Computing. Today I'm going to talk about the impact of Rigetti's CAPS-Diaz architecture on reducing crosstalk for our superconducting qubits. So the industry as a whole has been looking at 2Q fidelity, and in particular how that limits, how that's limited by crosstalk between qubits. And reducing that crosstalk is a subset of reducing contextual errors in general. Those contextual errors impacting both the 2Q fidelity, but also, in looking further down the line, impacting our ability to do error correction. So multiple different approaches exist. Pulse compensation is one of the active approaches, but that does not scale very well to large number of qubits. And so there's a focus within the community on how do we reduce the crosstalk at the chip level. So Rigetti in particular cares about AC flux crosstalk. And so the way that we tune the frequency of our qubits is using a magnetic flux. So we have a flux current that comes in, and if we look on the drawing on the right here, flux current that comes in, loops past qubit 0, and that induces a magnetic field which is captured by a squid loop, and then that tunes the frequency of that device. Now that same current that just flowed past qubit 0 flows along the edges of the ground plane until it flows to the grounds off the chip. And in the process can flow past other qubits and similarly induce a magnetic field into squid loops on other tunable qubits. And so when we're talking about crosstalk and quantifying that, what we're looking at is for a given flux bias that we're applying to qubit 0, then what's the percentage impact that we measure over on qubit 12? Essentially the effective flux that has gone through qubit 12 versus the flux that went through qubit 0 where we wanted to tune that qubit. And so to sort of give a sense of how this connects to QQ fidelities, we've done a set of calculations. I've got the reference here below, saying if you were limited by crosstalk for your 2Q gate fidelity, and in the worst case where you have both matched frequency and matched phase between qubit 0 and in this case qubit 12, then for a 95% 2Q fidelity, then you would need to get your AC crosstalk below 0.2%, 99%, you'd have to be below 0.1%, and 99.9, you'd have to be below 0.03%. So we can translate those just into a different measure, translate them into decibels. So 20 dB is a factor of 10 here. So the one sort of to keep in mind is the 0.1% crosstalk is minus 60 dB, correlates to the worst case limit of a 99% fidelity. So let's take a look at one of Rigetti's devices. So this is AC crosstalk on one of our deployed devices. It's been deployed for a little over a year now, designed about 2 years ago. And so what we're looking at is the full matrix between all the qubits. And so on the y-axis, you have the qubit that's being biased. There are 8 different tunable qubits in this lattice. And then on the x-axis, you have which qubit you're measuring the effect on. And again, this is in dB, so minus 60 dB is 0.1%, minus 40 dB is 1%. So as I said, AC crosstalk is what we use to actually modulate our qubits during use. But what we I'm going to be measuring in this talk is actually the DC crosstalk. And what you see is that it's actually a more sensitive measure of the crosstalk between the devices. So focusing on that, let's take a look at how we're doing. So if I just represent that crosstalk matrix as a distribution centered around roughly minus 40 dB, for this first generation device, this does not have a cap on it. It's just the QUIC, just our circuit chip. So as I said, the idea of the architecture that Rigetti has been pulling together is that we create a Faraday cage around our qubits, and that should minimize the crosstalk between qubits. And so we use a superconducting via, this is niobium coated through the circuit chip to connect the ground plane on the bottom side to the device side, and then we flip chip bond a cap chip on top of the circuit chip. And here on the left, you can see that we've got both cavities and a surface coated with niobium, and then we have indium bumps that are what we use to connect the cap chip to the circuit chip. So let's take a look at what happens when we add a cap. So here on the right, you see a picture of one of our cap devices. So the wire bonds are going to the QUIC from the PCB, and then you can see the cap sitting on top of the QUIC. So if we look at the bottom right at our crosstalk distribution, what we see is this cap device distinctly has a whole part of its population which is much better, much lower crosstalk than the Aspen 4 device, which did not have a cap we were just looking at. But there's also a whole set of qubits that overlap. And so if we look over on the matrix on the left here, what we see is that the measured qubit 12, whichever qubit we drive, we're getting an incredible amount of crosstalk on this particular device, a lot worse than, in particular, qubit 16, which should have the exact same design. And so we went and took a look, and actually in the layout, qubit 12 has a different design than qubit 16. So what we're looking at here is the red are the indium bumps that are what are going to connect our QUIC to our cap. We have a ground plane which on the QUIC, which the outlines of which are shown with the dashed lines here. And the blue is our actual circuit with the JJs connecting the center capacitor to the loop there. And we have coming in from the right, we have our flux bias current, which flows past our 2-qubit squid loop, and then off along the edges of the ground planes. So what you can see is that comparing qubit 12 to qubit 16, there's a bunch of indium bumps that are missing on the right-hand side of qubit 12. So we actually had purposely removed these indium bumps to avoid bringing the indium bumps too close to the edge of our chip. So looks like this might be a possible cause. So we went and fabricated a new set of caps where we now have a symmetric indium bump. So QC12 looks identical to QC16 in the layout. And what we see starting with the matrix on the left is that all of a sudden when we measure qubit 12, it's not sensitive at all, any more sensitive than any other qubit, especially compared to qubit 16. And if we look at our distribution here on the bottom right, what we see is that now we've shifted from, again, the red being the Aspen 4 with no cap, to this new cap device. We've shifted our median down much closer to minus 60 dB. So what we're seeing here is both the concept that using a cap with indium bumps can reduce crosstalk, flux crosstalk, but that part of the mechanism here is that we are moving the return currents from these flux biases, the currents that are flowing to ground, we're moving them off of the ground plane on the QUIC that's circulating past every other qubit and onto the cap ground plane. And thus, we're not giving a chance for flux to be created, magnetic flux to be created near any of the other qubits. So this approach is one of many that we're using to reduce crosstalk on our devices and is a fundamental part of our architecture. So looking at beyond just the crosstalk, the way we read out our qubit devices is that we're using resonators that are coupled to a feed line. And so we have a design level of this coupling, and if we measure what couplings we actually get on an uncapped device, we see there's this really wide distribution of that coupling coefficient. However, when we have a capped device, we have a very narrow range of that those couplings. And again, this points to what the cap is doing is it's really confining the E&M fields from our resonators, from our flux bias lines, from our qubits, so that we've removed, in this particular case, any parasitic capacitance that was also coupling the readout resonator to the feed line. So what tried to show here was that the architecture that Rigetti is using, this cap and via architecture, is enabling us to reduce our crosstalk at a fundamental level on the chip. Thank you.